In this chapter, we're going to take a very high-level overview of Hadoop's approach to big data. We're going to look at the history, where Hadoop came from and how it came into being. We're going to look at how it is both a parallel processing and a data storage engine. We're also going to look at how it abstracts all of the housekeeping away from individual developers. And we're also going to take a brief look at the costs involved. First off, some quick history. As many of you already know, Doug Cutting, the author of Hadoop, was busy creating a product called Nutch. Essentially, Nutch was an open source Google, which means it was two parts, a web crawler or a set of robots that went out and programmatically crawled through all the pages on the World Wide Web. And second, an indexer, which took all of the data that was pulled down and then went through each page, looking at the content and ranking pages in relation to each other. For example, on the AKC's website, American Kennel Club, if the web crawler hit it and pulled down a bunch of information, it might rank basset hounds as very highly relevant when a user searches for basset hounds. The crawler and the indexer processing was difficult. It was essentially a massive storage and processing problem. Doug needed some way to store all of the massive data that was coming down and an easy way to process all that data and do it in a parallelizable fashion. So as we see here with the timelines, as Doug was developing a paper in 2003, Google, a company that already had built an extensive web crawling and indexing engine, came out with two papers, the GFS or Google File System paper in 2003 and the MapReduce paper in 2004. Doug took a close look at what these papers were talking about and Google's approach, and he realized that Nutch could be totally re-architected. As he was re-architecting it, he realized that he had something unique that was maybe even more important than Nutch itself. And in 2006, he released the Hadoop project. In 2008, we saw Cloudera take up the call to be a services and support company for Hadoop, and they started packaging, providing support for, and providing consulting services around Hadoop itself. Somewhere in late 2008, Hadoop won a TerraSort competition. TerraSort was a bit of a badge of honor that the big supercomputing companies like Cray and EMC would pass back and forth every other year. The TerraSort competition involves how quickly a set of supercomputing resources could go through and sort a terabyte of information. It was essentially a benchmark to say who had the most performant system out there. When Hadoop came along in 2008 and won this competition, it put it on the radar of a lot of organizations, especially when they realized that it was free open source software running on commodity hardware, as opposed to the proprietary hardware and software that their current vendors were charging an arm and a leg for. In 2008, Cloudera both managed to hire Doug to the organization, and they were able to release CDH, the first version, Cloudera's distribution of Apache Hadoop. In 2011, finally they got some competition from a company called Hortonworks, which also provides services and support. Cloudera had a 3-year head start on them, and it's been difficult for Hortonworks to catch up. Hadoop is a rather strange name for a piece of software, and Doug actually got the name from his young son's toy elephant. In the beginning of Tom White's Hadoop the Definitive Guide, there's a great chapter where Doug goes into detail about why kids are so great at coming up with unique names. Doug has been a very busy individual. Hadoop is far from the only thing he does. For example, we know that Nutch, the open source web crawler, was also a Doug Cutting project. Nutch was his son's multi-purpose word for meal. When he woke up in the morning and he wanted breakfast, he would say Nutch. In the afternoon, when he was hungry, he would say Nutch. Again, a great, great name. Another of his projects, Lucine, actually came from his wife's middle name and her grandmother's first name. When you're looking for names for projects of your own, you may want to talk to your toddler or do some investigation of your wife's names. Let's next take a high-level look at Hadoop's design. It's essentially a distributed master-slave architecture. Some of the nodes in Hadoop are masters, some are slaves. We'll essentially have just a very, very few handful of masters and a whole bunch of slaves. It's also exceptionally fault-tolerant. As he was designing Hadoop, Doug baked in things like hardware and software going down on the slaves. He baked in things like network problems. He baked in issues of things like disks failing, network cards failing. As he was building Hadoop, he also tried to leverage the fact that commodity hardware is both extremely abundant and very, very cheap. Hadoop is meant to run on non-specialized or commodity hardware. Unlike systems that came before which used proprietary languages, Doug also made sure that it was written in Java, a mature common language that a lot of developers have experience with. Each daemon in Hadoop runs in a separate JVM or Java virtual machine. We talk about this more in another chapter. Doug was also very careful to make sure to abstract away all of the infrastructure and all of the undifferentiated heavy lifting from the developer. In Hadoop, the developers just think in individual key-value pairs. They write their code to consume and write out these key-value pairs. It also uses the MapReduce framework. We'll see this diagram many times in the rest of this course, in both this and other chapters. So when we say that each daemon runs in a JVM, let's talk about exactly what that means. Over here on the right, let's say that we have a slave node, an individual piece of hardware with its own disks, RAM, CPU, and so forth. JVMs are a Java, not Hadoop concept, and a JVM is a container in which the Java code runs. It could be the Hadoop core or the developer's algorithm. For example, we see here two Hadoop daemons. Let's say the data node and the task tracker, which we talk about in other chapters. This is part of core Hadoop, and these data node and task tracker daemons run in their own individual containers inside the slave node. These are long-running daemons that stay alive even when there's no processing. They're essentially the scaffolding that Hadoop uses to both store data via the data node and to process data via the task tracker. Again, we don't go into detail in this chapter what those are, but we're just laying the foundation of a JVM. The slave node also stands up short-term JVMs on an as-needed basis when processing needs occur. The task tracker is responsible for instantiating these containers and populating them with the map and reduce code, as we see here. The daemon and the developer tasks are now isolated from each other. Problems like individual crashes or out of memory or freeze-ups don't jump out of containers. So for example, if one of the map tasks went insane, it wouldn't affect the other tasks running on that slave node. Each JVM has its own dedicated memory, and each JVM is independently tunable. JVMs automatically do something called garbage collection, which means that the developer no longer has to individually manage the memory and collect it when it's free. There's also something in Hadoop called the Hadoop ecosystem. As anybody in IT knows, every system out there has storage and processing needs. These are common across projects and across divisions. The Hadoop ecosystem projects either assist with or enable the core Hadoop facilities, or they provide functions that were not available in the core. These functions are always related to storage and processing. You can learn more about this in the ecosystem chapter later on in this course. It's important to note that many of the ecosystem projects leverage the fact that as clusters grow, surplus storage or processing power becomes available, and users want to take advantage of that surplus storage or processing to do maybe other things on their stored data. Although we discuss MapReduce in detail in other chapters, let's just say here that there are many ways to write MapReduce code. For example, a developer could choose to write raw Java code, but it's hard to write this well. It is, however, the code that will always run the fastest. The important part here is to note that well-written bit. It's very easy for a developer to write bad code, and maybe even make the Java code run slower than a Hive or Pig query, which we'll talk about in a second. The second way to write MapReduce code is Hadoop streaming. This allows any developer to write map and reduce code in any language that they choose. Any language that can write to standard out and read from standard in. Last time I checked, every language out there lets developers write to standard out and read from standard in. It is important to note that inside of streaming, all of the other components, partitioners, combiners, etc., that we discuss in other chapters still have to be written in Java. There's also Hive and/or Pig. Both Hive and Pig provide a further processing abstraction, which abstracts away the details for the developer. These are covered in depth in the Hive and Pig chapters. It's important to note that if we start out with raw Java code and benchmark that as, say, 1, the Hadoop streaming will probably usually incur a 25 to 30% penalty, making it run 25 or 30% slower than raw Java code. Hive and Pig have been extremely optimized to run maybe only at a 10% penalty, and especially when you consider that that's a penalty with regards to well-written Java code, Hive and Pig are very powerful tools. In addition to providing a well-written abstraction layer for developers and a good fault-tolerant architecture, one of the big reasons that Hadoop has seen such widespread adoption is the cost involved. It simply doesn't get any cheaper than free and open source software running on commodity hardware. For anyone panning Hadoop and saying it's just a fad and will have something new in 10 years, just realize that it probably will never get more cost-effective than this. If another project comes out of the woodwork to replace Hadoop, it's going to probably have to do the same thing. In this chapter, we took a high-level overview of the Hadoop approach. We looked at the history, how it's both a parallel processing and data storage engine, how it abstracts out details for developers, and the costs involved.